Well, welcome to my first video of a video series in which I will present you my notes about finding independent sets, respectively maximum independent sets in graphs, and with the help of a decomposition approach. This will be the first part in which we will just introduce the basic definitions which we will use also later. You can find these notes and you can find the link to the notes below the video, like also possible additional material regarding this video. So let's start with our first part, basic definitions. We are interested, or at first we want to define what kind of stuff we are looking at all. And these are undirected and unweighted graphs. Assume, as long as we not mention anything else, we also will have this case in the beginning of our algorithm. Additionally, we also assume that we have a finite set of vertices, and what we will do during our algorithm will be that we will define a Riemannian manifold, and this Riemannian manifold will have a dimension which is given by the maximum degree what we have in our graph. So we will come to this part later. At the beginning, we are just talking about a Riemann, about a graph, an undirected graph. So we go to our first basic definitions, which is nothing exciting. It's simple, the definition of two connected vertices. In this case, we call them x and y. And we say if these two vertices are connected, then they are neighbors, and we write this in the following way. So respectively, n x be the set of all neighbors of x. So that's a simple case. So now the definition of a degree, I think everybody, if you know this, that's the typical thing. So that's the number of edges to which vertices belong to. So the number x, and we call it degree of x. We also, since we assume we have finite graphs, the maximum number of the maximum degree which a vertex of this graph can have is number of vertices minus 1, because we will also assume that we have no starting graphs, or better, we have starting graphs which no edges on themselves. Only edges to our vertices, but only in the graph at the beginning. During our algorithm later, we can have edges on themselves. So that's only our starting point. The next important thing is that we also will talk in the beginning that we have connected graphs. The algorithm also works with disconnected graphs. It's very simple to extend this on this case, but to keep this first explanation simple, we assume we have a connected one. And we assume also that during all steps we always have a connected one. But like I said, it would also be work for a disconnected one. So that's also what we have here in this remark. As long as we not say anything else, we say our current graph on which we are looking is connected. So the next important point here is now that we want to use for our algorithm Eulerian cycles. That's a very important point of this whole approach. So we should mark it. And say, okay, what we are looking here, this here is our important step, Eulerian cycles. So at first, let's think about, again, what is an Eulerian cycle? An Eulerian cycle in an undirected graph is a path which goes through our graph and uses each edge in this graph exactly one, and the starting and end point of this path is the same vertex. So we start at a vertex and go through all the edges and finally end at the starting point. So one important point is, of course, that this graph has to be connected, because if we have two disconnected parts, then for our algorithm we would need Eulerian cycle in the first connected part, and in the other connected part. In each disconnected part we would need a Eulerian cycle. But to keep it simple, like I said, we assume at the moment that our graph is totally connected, is connected, not totally, only connected. So we know that a graph G is Eulerian if every vertex of this graph has an even degree, or the set E of G is a set union of all edges of pairwise disjunct cycles. What we will use is this characteristic that every vertex has an even degree, and so that's the point where we have to look for. And like for the connected case, we also will assume at the moment, at first, to keep it simple, that our graph is always Eulerian. So that means all of its vertices have even degree. We will see that we also can extend our algorithm to the non-Eulerian case of graphs and subgraphs, because we can show that we can map the Eulerian solution, or we can map between the Eulerian solution and non-Eulerian solution of our graph approach for the total solution and for each substep. But also for the beginning, we want to keep it simple, so we assume also everything is Eulerian. So, at first. So after considering our basic situation, what kind of graphs we're looking at all, now let's look at a bit the kind of representation, how we can write down an Eulerian cycle of a given graph. Assume we have a graph, we know this graph is Eulerian, then it's possible to find the Eulerian cycle of this graph with Hierholzer algorithm, which is a polynomial algorithm, and finally we can write down this Eulerian cycle. So at first, what we have are vertex paths in generally. So what we do is we say, okay, it's in generally how we write down a vertex path. We go through a random path through our graph, and we can write it simple down according to the order how we went through the path. So let's say we look at a simple example of graph A, B, C, D, E. Let's say we go from A to B and from B to D. Then we would simply write A, B, D. So that's it. Assume next we denote Eulerian cycle. We have an Eulerian cycle. We now have the case that we know that we go through all of the edges of the graph, and finally we end again on the starting point after going through all our edges. So let's make an Eulerian graph here. So we have A to B to D, and then we can say let's go to D to C, C to B, B, E, and E, A. So 1, 2, and we go here, here, and the final edge which we take is this one. So we see we have an Eulerian path, and everything in this path has an even degree. A has 2, B has 4, C has 2, D2, and E2. So if we would write down this path now, we start at A to B to D to C to B, E, and A. So we see that each edge which we have appears exactly 1. The edge is always this thing here between. So we have here, for example, the edge BD, our second edge, or the edge BE. So it appears exactly 1. Additionally, if you have an Eulerian cycle, we always write this in the case that the first point, the first vertex of our cycle has to be also the last vertex, like here it's A. So B0, Bn minus 1 has to be the same thing. Yeah. Finally, what we also see is, of course, that's now this point here, that the way how we write it is not unique. We can also start, of course, at B and say we go at B, D, C, D, E, A, B. It's in fact the same Eulerian cycles, nothing else. That's all what we have here in this small writing regarding the permutation possibility. So then, given the Eulerian cycle, we have the thing that each vertex appears exactly degree half times. That's not very surprising. It's a simple thing that if you write here for example, C, which has two edges. So we have the one edge here, the other edge here, so it has degree 2, but it goes to left 1 to the left of it, we have one edge, to the right of it, we have one edge in this kind of writing. So it appears one time because it has degree 2. So finally, we want to what we call disruptive bitstring representation. This representation, what we do is we do a bit different kind of writing of the same graph. In this kind of writing, we write down again this complete sequence B, D, C, B, E, A, B, but we also kind of make a kind of 0-1 representation for certain parts or per certain subgraphs of the given graph G. This here is the whole graph G. And now assume we want to take a subset of vertices. Then we say, okay, we want in the subset, we want to have in the subset the vertex B. Then we say write a 1, and we say we don't want to have in our subset or subgraph the vertex D, and we write a 0 here, and then say okay, we also don't want to have C, but we want to have, for example, E and not A. So in this case, we would have the subgraph, which consists of the vertices B and E. That's what we call here disruptive bitstring representation. The intention for this kind of representation is now the given problem statement, what we want to look at. The given problem statement is we want to consider maximum or in generally independent sets. So what are the possible independent sets of our given graph G, which is this thing here? Yeah, we have the trivial ones, the elementary ones, A, B, C, D, and E. Then we have some larger ones. Let's think about, we could take A, but we could not take B or E, but we could take C, but not longer D, or we can take A with D. Our possibility, we take B, so no A, no C, no D, no E. So that's it. Then we can take C. We can take no B, no D, but we can take A and E. No, only A. So that's it. Or only E. When we look at D, we cannot take B or C, but we could take E or A. So we have D, A already, and we have D, D, E, the additional one. And yeah, can E not with B, not with A, E with C, or E with D. So that's all our possible independent sets. And the maximum independent sets would be in this case AC, ADs. Oh, we have a double one. It's of course only once. Yeah. So we have AC, AD, CE, DE, maximum independent sets. So, and our aim is to find an algorithm to find those maximum sets. So if we want to use our bitstring representation for this case, for example, we take AC, here, A, C. Then we wrote here, we take A, and we take C, but not D, B. So this would be the representation of A and C. What we now have to consider is the following, that the aim, or what we want in this kind of representation is we want to maximize number of ones in this kind of representation. So aim, maximize number of ones in a disruptive Bitstring representation. So what we have to care about is that, of course, a 1 is only count once. For example, we have a 1 here, we have a 1 here. It's the same vertex, so we would only count it, of course, once and not 2. So the maximum number of ones here is 1, first one, and the second. So we have 2 ones, and here we also have 1. Here this one and this one, 2 ones. Yeah. So because we have disconnected points here, have a we can make indices here 0, 1, 2, 3, 4, 5, 6, and then we say, okay, the bit at point at index 0 and at index 3 and at position 6 are connected in some ways, and the other things between are free. So this kind of representation gives us a possibility to look at this problem statement of a maximum independent sets in different ways, because we have a maximization problem of summation of numbers or counting of numbers. We can consider this we can interpret this as a bitstring problem, bitstring problem with disruptions. The other thing is we can consider the problem as a kind of connected spring system. And finally, more also according to the standard way, we have a maximization, a Boolean function maximization problem, Boolean function maximization problem. In the following of our presentation of this specific nodes, this different kind of ways of approach it we will not longer consider. We will focus on the content of this nodes, what we have here. But I will discuss the other ways, mainly this third one, and possible considerations for this in additional video series. In this video series, we only look at the content of those nodes. And for this specific nodes, we want to discuss approach, variation of a decomposition approach, which were already given, and which we want to expand to our way of considering this. So the next time we will go to the decomposition part of our nodes, and we'll look how this algorithm works. So thank you for watching. And if you want to support my work, you can find more information below the video for financially or other kind of support for my social media and so on. Thanks for watching and see you.